Both kinds of algorithms are relevant in the internet because it is a network of networks. In our picture, I've been drawing routers. Keep in mind that they represent whole subnets. So even in this cartoon picture of the internet, we imagine these routers as representing subnets like 197.42/16 and so on. In a given autonomous system, like AS8452 here, the routing within that autonomous system is managed by some organization, the one associated with that autonomous system. That organization is free to pick whatever algorithm it wants to set up routing within that autonomous system. A typical choice, though, is OSPF. That is a link stake algorithm that is based on Dijkstra's algorithm. And the end result will be some routing tables at each of these routers that say something like, if you're trying to get to the 197.40/16 subnet, then from this router, go in the down link here. If you are trying to get to 197.41/128/17, well, you need to get over here. Either of these choices might be okay, but it'll say go down, and then this one will say go up, and so on. So this is reflecting routing within the autonomous system. Routers within that autonomous system that connect to routers in other autonomous systems, those are called border gateways. So a border gateway is a particular role for some routers, ones that are connected externally. And that's the same border gateway as in BGP, Border Gateway Protocol. They have to participate in a specific protocol that everybody agrees with across all the autonomous systems. So that's what BGP is. To see how BGP works, imagine that in autonomous system 17055, a new subnet appears, 155.98.68. The configuration for this subnet then is published by that autonomous system using BGP to the other autonomous systems that it's connected to. So now, at the top left, AS8452 had some routing table so far, and it adds to its routing table the information that if you want to get to the 155.98.68 subnet, then you go down across that link. So any packet coming out of AS8452, now it knows where to send it to get to the new subnet. And again, this forwarding table entry was added as a result of getting a BGP message from AS1705. And this message you can view as a diff on the distance table in the Bellman forward algorithm. So this diff is very small compared to all the information that AS17055 may have published in the past. And it's all AS8452 and AS714 need to know to update their table to reach the new subnet. Internally, those autonomous systems will propagate messages among their own routers however they want to, but they're also obligated to pass on that information to other ASs that they are connected to, because this AS here on the left has no way to know that the one on the right already has a route to 155.98.68, but also it's possible that it's better for information to go this way than to go directly out of the top right autonomous system. We don't know. BGP messages let those networks make that decision. Having acquired that information now, if a packet is being sent from this subnet up here to 155.98.69, it will know its route out, and the lower autonomous system will know its routes internally, and the packet will get to where it's going.